mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning, grade 11s. Welcome to Wednesday, April the 15th. I hope you had a good day yesterday. We did a little bit of reading from our textbook. And today, I want to start you off with a verse of the day today. Yesterday's verse of the day had to do with loving others, and today's is similar in that. Yesterday, I asked you to think of practical ways in which you could love one another. Today's verse of the day comes from Philippians 1, verses 9 and 10, where it says, "And this is my prayer, that your love may abound more and more in knowledge and depth of insight, so that you may be able to discern what is best and may be pure and blameless for the day of Christ." So today's verse is a continuation of yesterday's theme of loving one another, and now we want to abound in that more and more each and every day, and be able to discern how that looks and how we can practically show that love to others. All right. Tomorrow, I want to do another video chat with you on Zoom, so I have already emailed you the link. I will put the link on Connect as well. It would be great to have all of you there. We'll just do a little check-in again. It'll be just a short time together where we can see each other's faces. You guys can ask any questions that you might have, and it'll just be a good chance to talk and to see one another. I'll put the link on Connect as well tomorrow morning. Yesterday you read about magnetic fields, and you read about the fact that moving charged particles create magnetic fields. And you were supposed to do a little bit of reading, and you were reading particularly about right-hand rules that give us the direction of magnetic fields. Because just like electric fields, magnetic fields have a direction. And so you had two right-handed rules, and I'm just going to quickly go over them here. And then we're actually going to introduce a third right-hand rule today as well. All right, so let's imagine this pen is a straight, long current carrying conductor, and that the current is running from this end to the other end, and our right-hand rule simply said take your right hand, put your thumb in the direction of the current, and then your fingers would curl around in the direction of the magnetic field. So that means the direction of the magnetic field would be a circle going in this way around the current carrying conductor. And it would be concentric circles. So the wire would be at the center. Concentric circles simply mean circles of different sizes with the same center. So it would just be here, and then you'd get bigger and bigger circles as you went away from the center of that circle. And so it would go in that direction. If we look at it this way, if I put my thumb that way, my fingers curl that way, meaning the magnetic field is a circle going in this direction around it. And a scientist by the name of Hans Ørsted was a scientist who developed these rules, or I didn't develop the rules, but he developed the theory behind the rules in terms of direction. And he did that by having current-carrying conductors, long straight wires with moving electric charges, right? Current is just moving electrons. And he would bring a compass nearby, and that compass would get directed in different ways depending on where he placed it in relation to the wire. Because as we talked about yesterday, compasses align themselves with magnetic fields. And so he could manipulate where the compass pointed by putting it in various positions around the current carrying conductor. The second right-hand rule you looked at had to do with something called a solenoid. Solenoid is just a fancy science term for a wire that has been coiled around something. Okay, so it's been wrapped around. Now this is just a pen now, not a conductor, and the pen doesn't have to be there at all. It's just a coil of wire, and the right-hand rule there simply gives us the direction of the magnetic field again. The magnetic field of a solenoid looks exactly the same as that of a bar magnet. So it has a north and a south pole, and the magnetic field lines surround it exactly like a bar magnet. And so the right-hand rule there gave us the direction where north was based on the current. Okay, we're not going to do anything with solenoids this year, but next year we'll do significant work with solenoids as they are the foundation and the basis of what are called Faraday rings and transformers. So we'll do more about that next year. All right, today we want to talk about now the force. If we have a current carrying conductor with its magnetic field, and we're going to put that into another magnetic field, or we're going to bring it in close to another current carrying conductor with its magnetic field, there's going to be a force of attraction or a force of repulsion. And we're going to look at what the magnitude of that force is today. So we're going to do that on the whiteboard. So we'll head over there now. So over here on the board, we're going to talk a little bit about the force. When we place a current carrying conductor in a magnetic field. And so again, Oersted was a scientist who pioneered this, and what he did was he took a current carrying conductor, a wire, and he put it between the ends of a bar magnet. And there's some very good pictures of this. I can't draw them, but there's some very good pictures of this in your textbook on page 652 and on page 653. I'll refer to you that to those pages a couple of times today. So it'll be a good idea to check those out. So he placed a current carrying conductor between the ends, the prongs of a horseshoe magnet. Sorry, I think I said bar magnet earlier. A horseshoe magnet. And so on a horseshoe magnet, you have one north pole, one south pole. There's a magnetic field that runs from north to south, and he would place a wire in between those two tines. And what he realized was that the force, the wire, the current carrying conductor would experience a force, and it would go in a certain direction, and it would have a certain magnitude. Now, just a couple of terms before we get too far into this, and a couple of symbols that we have to be aware of. Okay, we're talking about current, we're talking about a wire, which has a particular length, and we're talking about magnetic field, all right? So force, we know, force is measured in newtons, we know what that is. But current, if you don't remember from a previous science course, current, the symbol for current is I, capital I, and it is measured in amps, which is a symbol is an A. And the length of the wire is, again, it's in meters, it's a length, standard unit is meters. A magnetic field. All right, so magnetic field, the symbol for magnetic field is a capital B with a vector sign. It is a vector because it has a direction, and it is measured in Teslas, which is a capital T. Now you'll recognize the name Tesla. He did a lot of pioneering work in electromagnetism as well, and so he has a unit for magnetic field. All right, what Oersted found as he was researching this and experimenting with this was he found three things. He found that the force on the current carrying conductor was directly proportional to the current. Greater the current, greater the force. He also found that the force was directly proportional to the length of the wire that was in the magnetic field. And so, again, more of the wire in the magnetic field, more length gave us a greater force. And he also found that the force that the wire experienced was directly proportional to the magnetic field. Stronger magnetic field meant stronger force. And again, this all makes perfect sense, right? He also did find that the angle between the wire, the current carrying conductor, and the magnetic field made a difference. Most of the time, pretty much all the time this year, our angle is going to be 90 degrees. Our current carrying conductor and our magnetic field are going to be at right angles to one another. And so what that gives us is it gives us this formula. The formula is the force, the magnetic force, or the force between on a current carrying conductor and a magnetic field is equal to B, magnetic field, times the current, times the length, times the sine of the angle between the two. Now again, almost all of our questions this year, the angle is going to be 90 degrees. They're going to be perpendicular. And if I put 90 in for theta, the sine of theta is just 1. So it disappears from the question when theta is 90. So it really becomes F equals BIL. F equals Bill, if you want. And so that gives us the magnitude. It's a fairly simple formula, right? Just straight multiplication. Okay? I should be able to give you 3 of these 4 pieces, and you'll be able to find the 4th. And there's an example that I'll refer to you in your textbook momentarily that you can read before doing some questions on it. But because it has a magnitude, it must also, and it's a vector, it must also have a direction. So let's talk about direction on the next whiteboard. All right, here we have some statements on direction. And again, can't draw very well. So again, in your textbook, on page 652, there is a much better diagram than I could ever draw. So we're just going to talk about it here, and then you're going to go to your textbook and check it out on page 652. And it refers you to a diagram that's actually on page 653. But the right-hand rule is this. Now, we have three different things. We have current, we have magnetic field, and we have force. Those three things will be at right angles to one another. And so when we do our right hand rule for this one, we're gonna hold our hand open like this, okay? And as you see on the board behind me, what we're gonna do is we're gonna place the thumb in the direction of the current. So whatever direction the current's going, that's where our thumb is gonna be, okay? Our fingers, our extended fingers, we're holding our hand like this, thumb's current, extended fingers point in the direction of the magnetic field. Okay, if we set that up properly, then the force will be in the direction that the palm would push. So if I had my hand on the board here and I had a current that was going up the board and I had a magnetic field that was going in this direction, okay, I put my thumb in the direction of the current, my fingers are in the magnetic field, the force would be pushing out of the board. Okay, so we have to think in terms of three-dimensionally here. Okay, thumb is the direction of current, finger is the direction of magnetic field, palm pushes in the direction. Okay, same thing if I all of a sudden changed it and held my hand. Let's go this way. Let's say the current was coming out of the board and the magnetic field was up the board, then my palm would push that way, okay? And in my case, it's to my right. If you're looking at this, it would be to your left, okay? But it's in that direction. All right, so that's the direction. So we have magnitude on the other board, F equals BIL. We have direction, using this right-hand rule for the force, giving us a direction. And that's all I want to leave with you today. There are some questions on page 654 that I want you to do. There's an example, a sample problem that walks you through giving some information and solving for a piece in that formula, F equals BIL. And then there are some questions that I want you to do. I'll put the page number and the question numbers on Connect. Check it out, give them a try. As always, email me any questions that you might have. And again, tomorrow at 11 a.m. we're going to, actually that'll be today. I'm recording this a day early. So on Wednesday, today, at 11 o'clock, we will be having a little Zoom meeting. So again, check Connect and your email for the link to that video chat. Have a great day. We'll see you later.